This video is going to be about fields. So we'll talk about scalar fields and vector fields, and I'll give you two specific examples of fields that you encounter every day, and just kind of using all the vector math that we've built up this semester to describe these fields. So in order to understand and be able to deal with this concept of a field, we're going to apply these specific vector concepts. So you need to be able and feel comfortable dealing with any of these four vector concepts here, understanding the difference between a vector and a scalar, creating a unit vector that describes the direction of a particular vector, finding the norm of a vector, and also describing a location in space using a position vector. So if any of these things seem a little foggy to you, I would pause this video now and go back and review those topics. So the first topic here is something we want to try to differentiate between a scalar field and a vector field. So a scalar field, it describes the value of a particular scalar quantity at every location in space. So the thing that makes it a field is that it's showing the value of this scalar quantity as a function of position. So here is an example as a temperature map. So when you look at the Weather Channel and you see this temperature map for for a particular location, a country here, you can see the value of that scalar quantity of temperature at various locations in space. So that's what makes it a field. If you just measure one temperature, like wherever you are, that's not a field. When you show it as a function of space, now we have a field. And this in particular is a scalar field. Remember that a scalar is a number. It can be positive, negative, or zero. So it's totally fine to have like a negative temperature. Scalars can be negative. We're going to focus though on vector fields. We've been, building up all of this math that we've been doing this whole semester about vectors. So let's just jump right into the good stuff. This is a vector field. Again, it's showing a magnitude and direction of a particular vector quantity at every location in space. So again, the field aspect of it is the fact that we're showing these vectors as a function of position. So each of these locations has a different vector magnitude and direction. Some of them are the same, but it can change. It varies as a function of space. So here when you look at, again, maybe you're watching the Weather Channel and they show you wind velocity. Velocity describes how fast something is moving and in what direction. So this map is showing you the magnitude and direction of the wind velocity vectors at every location in space. So this is a vector field. We are going to focus on two specific vector fields. The origins of these vector fields have to do with an intrinsic property of a particle. So these are just two specific examples, like I showed you a temperature map or a wind velocity map. Those are vector fields. But the ones that we're going to talk about are generated, or they exist because of intrinsic properties of materials. So the first one we're going to talk about is gravitational fields. And this field occurs because of mass of particles. So that's the property that these things have, and it generates a field because of that. The other one we're going to talk about is the electric field. This one is due to the intrinsic property of electric charge. And so just by the fact that objects have these properties, they actually create fields. And these fields change as space, like as functions of space. And so you can actually create a map that shows the magnitude and direction of these fields at every location in space. And because of these fields, what's really cool here is that because these fields exist, then objects that possess these properties can actually interact with each other without ever actually touching each other. So this is what's kind of cool here. We'll give you a little bit of physics to explain what's going on. But again, it's always going to be presented in the context of the vector math we've been discussing so far this semester. So everyone kind of has a superficial idea of what a force is. Like when you push on someone or you pull on something, that's a force. It's an interaction between two objects. There are two different types of forces. One is called a contact force, and then the other type is a non-contact force. So when you touch something, when you press on it, that's what we call a contact force. Like two objects, their surfaces are interacting with each other. The ones that we're going to focus on, these are kind of the more interesting to me at least, types of forces, the non-contact forces. It's when two objects are actually interacting with each other. They're exerting forces on each other, and yet they're not touching each other. And the way that they're doing this is using their fields. So like in this picture here, you have two objects, and each of them, because they have the intrinsic property, let's say of mass, they each have their own gravitational field that extends and like changes as a function of space. And because these fields are overlapping with each other, now the objects can actually interact. They can exert forces on each other, which lead to motion. And so you can see the motion of these particles. It's all because of this interaction between their fields. That's the type of fields that we're going to focus on here. This is an example here. It could be a gravitational field or an electric field. So let's start off with gravitational field vectors. The symbol is a little lowercase g. This is the gravitational field. You may also hear it described as the acceleration due to gravity. It might be confusing to you. I'm just going to call it the gravitational field vector, but they're kind of interchangeable. So this is the acceleration due to gravity. But really, I think the better description here is it's the field created by this gravitational property. So the units are newtons per kilogram, or that actually simplifies, if you know what a newton is, it can simplify to a meter per second squared. So either of those units is fine for this gravitational field vector. When I describe this as, it's a disturbance in space surrounding a particle that possesses mass. So let's say we're talking about a specific particle, mass m. Whatever mass that object has, it creates a field due to just possessing that mass. And that field, it like fills all of space around this particle. And so this field has a different magnitude and direction depending on where you are in space, how close you are to this object, mass m. And so typically whenever you see a particular gravitational field vector, you'll see like a little subscript, you might see a little subscript on there that describes what mass is generating this field. So if you see the subscript here, that's what that means. It's not telling you about like a vector component of this thing. It's telling you about what object created this field. So try not to get that confused there. I understand that might be confusing when you've been seeing subscripts that kind of tell you about directions like X or Y or Z. M is not a direction. It's telling you what mass is creating this field. So because these fields have different values depending on where in space you are evaluating the field, we have to define a particular location in space at a time. We figure out what the field's magnitude and direction is at that particular location. Now we have one point. We have one arrow that we can draw at that particular location. And now to create the entire vector field showing how this vector changes throughout space, now we would evaluate other locations in space to actually build up this vector field showing the gravitational field vector. So to define a particular location in space, we need a position vector. Position vectors start at an origin and they point to a location in space. So right now I am placing my origin right there on this particle that's creating the field. So for all of these definitions that I'm giving you here, our origin of our coordinate system is always right on the particle that creates the field. And you can use this equation here to figure out what the gravitational field vector looks like at this particular location in space defined by the position vector r. We'll talk a little bit about what all these constants are in here. We're not going to go too in depth this semester, so don't get hung up too much on like memorizing what this, G or M or anything like that is. Just kind of take the equation. We're going to talk about different features of the equation. Remember, this is something you definitely need to know, and you should remember this from our earlier recordings. Any vector can be expressed as its magnitude times its position vector. Any vector is a product of its magnitude and direction. So vector r, this position vector, can be written as the norm of vector r times unit vector r. And you'll notice here in this equation for gravitational field, you'll see the norm of vector r right there, and you see unit vector r. So these are related to position vector r. Okay, just remember that relationship there. The other physical constants that you see in this equation, one of them, that capital G, that's just called the universal constant of gravitation. It's just a number. You do not need to memorize that number. Just the fact that it is a positive scalar is what you need to recognize here. Like I said, R is just defining this location in space, and so this gravitational field vector, you can look at the equation, it depends on the mass of the object that's creating the field and where you are relative to that mass. So that position vector, the magnitude of that position vector tells you the distance from how far you are to that mass. And so that's, just remember that this particular field vector describes the gravitational field at that one location in space. And just to make it really clear here, so we're defining one location in space at a time to then compute the gravitational field vector at that location due to this mass right here, m. And we need the unit vector that describes the direction of this position vector. The unit vector is what appears in that equation for the gravitational field vector. So just make sure that you feel comfortable. If you know the position vector, can you construct the unit vector? If you remember this equation here, you should be able to see that the unit vector would just be the full vector r divided by its own magnitude. And that's how you get the unit vector. Remember, they have the exact same direction. They just have different norms, because the definition of a unit vector says that the norm of a unit vector has to be the number 1. All right? Now, we can use that equation and we'll get the gravitational field vector at that one particular location in space. To build the vector field, to show what it looks like as a function of all of space, you then need to move to another location, compute that gravitational field vector, and just kind of keep on going until you have all the locations in space, and you draw these vectors at each location, and that's how you build the gravitational field. And you can kind of see what it looks like in all of 3D space. So here's a picture here that shows you the gravitational field created by this little blue mass that's at the very center, our origin of our coordinate system, and you can see the various gravitational field vectors at each location in space. Notice that the lengths of each vector changes as you get further and further away. As you get further away, these lengths are getting smaller, which tells you that the magnitude of this gravitational field vector is getting smaller and smaller and smaller as we move away from this mass that's creating the field. And notice the directions of all of them. They kind of point all towards that mass. And we're going to talk a little bit more about why all of them have that similar direction of pointing right at the mass that's creating the field. All right, so let's do an example together, calculating the gravitational field vector at a particular location in space. So we need the equation. Let's just remind ourselves the gravitational field vector is negative, capital G, which is the universal constant of gravitation, times the mass of the particle that's creating the field, divided by the norm of our position vector squared, times r hat. All right, so I see vector r. So in order to get r hat, I need to know what vector r is in component form. Then I can get the r hat vector from that. So let's put vector r into component form. So I'm going to redraw my unit vectors tail to tail with vector r, and think about the angles that these vectors make with vector r. So angle alpha is the angle between x hat and our vector r. I see 59 degrees plus 90 degrees. That's 149 degrees. Angle beta is the angle between our vector r and the y hat unit vector. So that would be like 180 minus 59. So that's 121 degrees, I believe. And angle gamma is just going to be 90 degrees because z hat is coming out of the board, and our vector r lives on the plane of the board. So those are automatically 90 degrees to each other. So I have my angles. Now I'm going to put that into component form. So vector r is the norm of vector r times cosine alpha times the norm times x hat. So let's plug that in. 0.5 meters. Cosine of alpha was 149 times x hat, plus the norm of vector r times cosine beta, which was 121. All of that times y hat, plus the norm of vector r times the cosine of gamma, which was 90 degrees, times z hat. That's putting a vector into component form using the generic expression for a vector in component form. I just plug in those numbers now, and I can get my vector r in component form. So I get negative 0.858, or sorry, no, that's not right. Negative 4.29 meters, x hat, minus 0.258 meters, y hat. So that's vector r in component form. That's step number 1. But I really wanted r hat, because that's what's appearing in my equation there is r hat. R hat is just vector r divided by the norm of vector r. So that's just this vector we just described divided by its norm, which we know is 0.5 meters. So you want to divide each of those terms by 0.5 meters. And when you do that, you'll get negative 0.858 x hat minus 0.516 y hat. Notice that the meters are gone because I divided terms like 0.429 meters divided by 0.5 meters. Both of those canceled out. And so my unit vector has a norm of 1 without any units. So like no unit vector should ever have units in them. They should just be pure numbers times unit vectors. And then when you find the norm of this vector, you'll see that it equals the number 1 without any units in there. Okay, so make sure you understand how to get a unit vector from an existing vector. Now that I have that, I can just kind of plug all of this stuff in to my equation to calculate the gravitational field vector. So negative capital G is just the number 6.67 times 10 to the negative 11th. It has units of newtons times meters squared divided by kilograms squared. Then that is times the mass of my particle, which was 100 kilograms. All of that is divided by the norm of r squared, so that's 0.5 meters squared. And then all of that is times r hat, which was negative 0.858 x hat minus 0.516 y hat. Make sure your x hat and y hat are still there because vector r hat is a vector. Do not plug in the number 1. That would be confusing a vector with its norm. So just be really careful. Our final answer should be a vector in component form. If you go through the math and multiply all this stuff together and then distribute it to the things in the parentheses, your final answer should be something like negative 2.29 times 10 to the negative 8th newtons per kilogram x hat minus 1.38 times 10 to the negative 8th newtons per kilogram y hat. So that is a vector in component form. That's the gravitational field vector at that location in space due to mass m. So let's look a little bit more conceptually without actually plugging in numbers here. Let's just look at this equation a little bit more. Let's think about the norm of this equation and the direction of this equation separately. So this is a vector. It has a norm and it has a direction. Let's look at the norm. When you're finding the norm of any vector, you're going to dot the vector with itself and then take a square root. So I've written that down. I've plugged in our form for the gravitational field vector, dotting it with itself, taking a square root. All of the constants in front, the g, m, norm of r squared, all of those are just scalars. So you can kind of pull all that stuff out to the front. When you multiply all those scalars together, the negative signs go away. And then it's all of those things squared, but you're taking a square root. So just kind of pull all that stuff out to the front. Really what you have left is all of those constants times the square root of r hat dotted with r hat. Now r hat is a unit vector, and the angle between this vector with itself, of course, is 0 degrees. And so really in the end, when you take the square root of 1 times 1 times 1, in the end, the expression for the norm of this vector is really just all of those constants that were out in the very front, but without the negative sign. So it's g times m, the mass of your particle, divided by the distance squared. So that's the norm of the gravitational field vector. If you're ever just interested in just the norm and not the direction, you could use this equation to just focus on the magnitude of that vector. Now, we could rewrite this vector, g sub m, would be equal to its norm times its unit vector that describes its direction. So when you compare that to what we have in the like in this box right here, notice that this unit vector that would describe the direction of g sub m is exactly equal to negative r hat, because that negative sign is still out front. All of these things just described the norm of the vector. So negative r hat describes the direction of this vector. And so negative r hat, well, that would just be in the exact opposite direction as r hat. So all of these gravitational field vectors, they actually point towards the particle that created the field, because r hat points away from that to the location in space, and so negative r hat points right back towards the particle that created the field. So that's something kind of interesting about gravitational field vectors. They always point towards the particle that created them. I know that was a lot of information, and now we're going to kind of very quickly apply it to a different type of field. You'll see a lot of similarities. Again, don't get kind of lost in all of these quantities. We're just focusing on the vector math aspects of it. Just kind of showing you a cool application of all of these things. Another field is called the electric field. This one is generated due to the electric charge of a particle. So charge is given the symbol Q, like a little lowercase q. Sometimes in chemistry they say uppercase q, but I like to use a lowercase q. Again, you can put a little subscript on there that names the particular particle you're talking about so that you can now match it with the field that it generated. The equation for this electric field, you'll notice, looks very similar to the equation for the gravitational field. A few things have changed. That constant that used to be capital G, now it's just little lowercase k, this is called Coulomb's constant. It's just a number, it's a positive scalar. Q sub s, that's the electric charge of the charge that's creating the field. R, like the norm of R, is still just describing the distance you are from that particular charge. And r hat is the unit vector that describes the direction of the position vector. So we're still describing one particular location in space, and we're evaluating the field, the electric field, at that location right there. So you draw the position vector. Again, the origin is right there on the particle that's creating the field. So the position vector points from that particle towards a location in space. You can describe the norm of that position vector and the unit vector that shows you the direction of it. So all of the same principles, all the vector math is exactly the same here when you're talking about electric fields. If you understood the gravitational field stuff, now you're just seeing it again, just due to electric charge instead of mass. So really just kind of look at these two equations here. There are obviously some differences. One of the major differences to look at is that notice there was this negative sign for the gravitational field. There is no negative sign in the electric field. So that's one big difference. Another big difference that is kind of related to this is the fact that mass is a positive scalar, but charge can be positive or negative. So earlier when we were talking about like the direction of the gravitational field vectors, they always point towards the mass that created them, because like all this stuff is just positive scalars, so the negative sign reverses that direction. So gravitational field vectors always point towards the mass that created them. The difference though here with electric field vectors is that because charge can be positive or negative, that means that the electric field can point towards that particle or away from that particle. So it really depends on what the particle is that created the field. That will determine the direction of the electric field vectors at every location in space, whether they're pointing away or towards. Those are your two options though, because our vector r always starts at that particle and points towards a location in space. So just kind of keep that in mind. It's again, it's just vector math. You have the option of a positive scalar times r hat, or positive or negative times r hat. So it's just kind of an interesting feature, and it's just coming from vector math. One last thing I wanted to talk about was adding these vectors. You're allowed to add vector fields. Obviously, there's never just one mass in in some location. There's lots of mass, there's lots of charges. And so to find the net field at a particular location in space, you can find the individual fields created by the individual particles. Net just means the sum of all of these different field vectors. So if you have multiple fields that exist at one particular location in space, then you can add those fields that exist at that location in space, just like you can add any other vector together. So let's do an example here. Let's say that there are multiple charges surrounding, they exist, and because of that, these three field vectors exist at one location in space. So they're kind of all overlapping each other, and we want to find the sum of these three vectors. You can find this graphically, or you can do it in component form, kind of depending on how much detail you need. Let's just do it graphically right now to visualize E-net. So to add these vectors, I'm going to place them tip to tail and draw a resultant. So E1 plus E2 plus E3. Now I've placed, that's my train of vectors that I'm adding, and so now my resultant vector starts at the tail of the first one and points to the tip of the last. There is my resultant vector E-net. Notice that E-net is not tip to tail with all the vectors being added because it represents the sum of those vectors. So now we can visualize what E-net looks like. You can kind of get a gauge for how long it is relative to these other vectors and its direction. It definitely exists. So you can see that, just kind of seeing those things graphically. I don't have any detailed answers about the component form of it. We would have to do that in component form. So I will show you that, but we're not going to really have time to go through this full example. So if you wanted to actually, compute this net electric field vector and get a number to describe its magnitude, let's say that that's the problem that you're being asked, then you would need to probably not use the graphical method, but use the component form method. So I'm not going to fully work this problem out for you. I think this is a really good exercise for you to do on your own. I will give you some direction just to kind of remind you. Please, please, please do not make the mistake of thinking that the magnitude of the net electric field vector is equal to the sum of the magnitudes of the vectors that are being added together. So this is actually an intolerable error. If you do this, you get 0 points. The net electric field vector is the vector sum of E1 plus E2 plus E3. So the magnitude of E-net would actually be the magnitude of that vector sum. You have to add the vectors first. So it would be the magnitude of, first you have to add the vectors, E1 plus E2 plus E3. And then once you have that answer, then you find the magnitude of that resulting vector. So do not mess up the order of operations here. It's very important to see why you have to do it in this order. But here are my hints as to how I would solve this problem. First, I would put each vector into component form. Then I would add the vectors in component form to get the net electric field vector. Then I would use the definition of the norm to get the norm of that vector. All right, so that's your guidance on how to solve this one. This is a really good final exam style type of problem. It's combining a lot of concepts together, so I highly recommend that you try putting this one to pen and paper. Sit down and see if you can get that answer. The answer is shown on the conceptual reference material page, so you can always check your work there.